Well, thank you, everybody. We're really happy to be here to talk about our tiny but mighty observatory, SPHEREx. Phil and I have been working on this for about a decade, from initial concept and all of the evolution of that into the wonderful observatory that just launched in March. And we're really happy to talk about the evolution that brought this mission to life and the observatory that is right now in space taking data that will revolutionize the astronomy community over the next decade. Okay, so SPHEREx has a proud history with the tortured acronyms of NASA. It is the spectrophotometer for the history of the universe, epoch of reionization, and ICE's Explorer, but you can just call it SPHEREx. I know it's a mouthful. We really wanted the sphere in the name because we are going out and making an entire map of the entire celestial sphere. We're an observatory that doesn't look down at Earth, but out at space, and we're really observing the entire sky outside of Earth. We're part of the proud history of the Explorers Program Office in Astrophysics and Heliophysics at NASA, and you can see an evolution of those missions across time. And we are in the medium Explorer class. This is about $350 million cost cap to NASA, and really doing incredible science in astrophysics and for the sun over the years. So we slot right in there between some of our brethren in the astrophysics fleet, and are really proud of that. These are currently the largest principal investigator-led missions for scientific exploration and astrophysics at NASA, and there are approximately 2 opportunities per decade. So we got our opportunity this decade, and are really proud to add SPHEREx to the fleet.
All right, thanks, Jen. So indeed, SPHEREx is an all-sky infrared survey. This follows in a series of missions, both from the ground-based and from orbit as well. This is an image composite built up of several previous missions spanning in the near infrared. This includes the NASA missions, IRES, and COBE, as well as some ground-based 2MASS. And all-sky survey missions are really a cornerstone of modern astrophysics. They continue to garner tens of thousands of citations, reaching a broad range of science topics, and really support the community with their archival properties. Now, all of these images that we're showing here across the infrared are in broadband continuum wavelength bands. So you have some spectral information, but it's really washed out in these continuums. SPHEREx is going to provide an all-sky survey, but spectroscopically. So for every single 6.2 arcsecond pixel on the celestial sphere, we will deliver 102 wavelength across the near to the mid-infrared. And really, if the old adage is that a picture is worth 1,000 words, a spectrum is really worth 1,000 pictures. There's just so much more information that you have in spectroscopic data sets. Within the framework of this all-sky spectroscopic survey, we have optimized SPHEREx to tackle 3 really profound fundamental questions. These flow down from the priorities set forth by NASA, as well as in the decadal surveys, and they are grandiose indeed. What are the conditions for life outside our solar system? How did galaxies begin? And how did the universe begin? So enormous questions indeed, and SPHEREx, I'll walk you through how we're going to address, really make significant contributions to these profound existential questions that we ask ourselves. So let's start on the largest scale thinkable, right? How did the universe begin? Okay, well, if we look here on a cartoon of the history of the universe as we understand now, time flows along that x-axis, and at each epoch in time, the cross-section of the cylinder represents the scale factor of the universe at that time. So we move along from the Big Bang as the universe cools, measurements of the microwave background, that relic radiation from the time when the universe first became neutral and hydrogen atoms form. Cosmology has learned so much from studies of the microwave background. It really gave birth to the idea of precision cosmology, where we could make very, very precise extractions of the universe's contents from studying this fluctuating field in the microwave. Now, there are 2 observations that came out of the microwave background that really are profound but provoke further thought. The first observation is that the universe is entirely uniform on the largest spatial scales. its spatial geometry is also flat. Now, these may seem trivial, but they are not at all predicted for any kind of special scenarios of universe formation. So in order to get at this, how could these regions that are completely causally disconnected on the largest scales be in thermal equilibrium to such a fantastic degree? To get at this, in the early 80s, the theory of inflation rises as the best explanation of this. And I love this figure. This is from Alan Guth in 1980. If you look at this figure, which plots the size scale of the universe as a function of time, there are 100 orders of magnitude on that logarithmic y-axis and a similar number on the x-axis. And as that plot implies, the theory of inflation posits that the universe, at just 10 to the minus 32 seconds after the Big Bang, underwent a period of unbelievably rapid expansion, expanding a trillion-fold in that tiny fraction of a second. It's hard to wrap our brains around what a number like 10 to the minus 32 seconds after the Big Bang means. Think about it this way. We're at 10 to the 17 seconds since the Big Bang now, right? So 10 to the minus 32 to 1 second is a much longer time than 1 second after the Big Bang to now, right? So there's still a lot that we don't know about inflation, right? This theory has held up to all the observational predictions so far, but what was the energy scale like that drove inflation? How can we get at that? Well, if we look at the universe today, you see a map that looks like this. This is an actual data set from a ground-based predecessor called DESI, and every single dot in this image is a galaxy, each with hundreds of billions of stars in it, right? And what you notice from this is that the distribution is not random. It's highly clustered and forms into what we call the cosmic web. There are these filaments, overdensities and underdensities, voids. And so where did this structure arise from? The answer to that is actually really quite profound. If we think about going back to that early epoch right after the Big Bang, the entire universe is smaller than the size of an atom. As such, it's governed by the laws of quantum mechanics, and we have little quantum fluctuations in that matter field, little overdensities and underdensities that fluctuate in and out of existence. Now, as the universe expands, grows in size, cools down, those little tiny imprints from quantum fluctuations become stretched out to the largest scales imaginable. And in those overdensities, that's where matter forms. That's where stars ignite and the first galaxies evolve, and then the universe expands and cools later, and we're left with this cosmic web, this large-scale structure that has been set up in those initial moments after the Big Bang. So that means, if we go back to our picture, that the best way to get at those first epochs, 10 to the minus 32 second after the Big Bang, is by measuring the large-scale structure of the universe today. And the way we do that is by obtaining spectroscopic redshifts to about 400 million galaxies. If you think about it, what the cost of SPHEREx is like, that's less than $1 a galaxy for spectroscopy. It's a tremendous value and a tremendous data set. Moving on to our next science theme, if you now think about that same evolution of cosmic history and now ask, what is the history of light production? Well, we get at that from a signal called the extragalactic background light, and it's just that. If we just look in any direction in the near infrared, you're looking at the integral of all the photons that have been emitted since the dawn of the universe, since the epoch of reionization, those first stars lighting on. At high redshift, or the early universe, those are rest frame UV photons, which then get redshifted into the near infrared when we look at it. Also, nearby in the galaxies, there's diffuse faint glow from stars which have been flung out to the outskirts of their host galaxies and make this diffuse glow. So SPHEREx uses a technique called intensity mapping. And now if you think about that matter field again, and we talk about a galaxy survey, we're just looking at the bumps at the top of the density field, right? You look at a galaxy survey, that's what you're measuring. But there's so much more signal there all the way throughout the filaments from various different contributions throughout cosmic history. So we use intensity mapping and make these deep maps of this fluctuating light field, and through spectroscopy, we separate out that light field into all of these wavelengths, cross-correlate between them spatially and spectrally, and with that we can begin to disentangle the composition, the history of galaxy formation and evolution, how much light comes from whatever redshifts and whatever species, spectral lines, everything is in that light field. And we're going to study that with precise statistics. Moving closer to our own neighborhood, another, one of the most profound questions we can think about, getting at the origins of life. As far as we know here, all life that we know about requires water to exist. And if you think about the distribution of water in the universe, the vast majority of it is not liquid. It is ice. So what SPHEREx is going to do is look at millions of lines of sight along our galactic plane with background stars and look at the absorption spectra in the near infrared. Water ice has this big old absorption band at 3 microns, as well as a whole bunch of other biogenic ices, other ices associated with life. And we're going to survey the entire galactic plane. And just along with that, when you do spectroscopy on such a large scale, everything falls out. Every 6 arcsecond pixel will have a spectrum in the near infrared, and this data will come out to the community. So anything you care about having spectroscopy on, large number statistics on, we are going to provide. As long as your object is above our detection threshold, we are going to deliver to the community a spectrum of that object across the near infrared. With that, we'll switch to more of the implementation of SPHEREx.
So I think the science speaks for itself in its ambition, and it's really impressive that this tiny little mission is going to address a whole bunch of these really fundamental questions in astrophysics. So you might be asking yourself, as I was at the beginning of the proposal for SPHEREx, how do I build an observatory that does all of this? Doesn't it sound hard? It sounds hard. So this is our observatory. It's a cutaway view, obviously, with the 3 photon shields cut off in the front so you can see the telescope there in the center. But our tiny little observatory is only about 2 meters high from top to bottom. You can see our spacecraft there on the bottom, and I'll talk about that in a moment, and then the payload from the spacecraft bus all the way up, and our passive cooling system. The most important part of SPHEREx to enable the instrument to operate in the infrared and take these measurements that Phil described is that it has to have really great thermal performance. We're at 650 kilometers of altitude above the Earth. It's pretty warm there by space terms, and so we had to really think about the thermal architecture of the system, and that was a central part of our design for this observatory to make it really conducive to operating in the infrared. So our observatory does not have any propulsion. We actually are fully dependent on the injection of the launch vehicle and then slowly decay over our lifetime. And we do decay within 25 years, but spoiler alert, we can go way beyond the prime mission and still do great science. We're pointed through inertial measurements with reaction wheels, and we don't have any moving parts in the instrument. And no moving parts on the rest of the spacecraft. We literally just use the reaction wheels to point and do every single observation that is planned in the science mission. We communicate through the Near Space Network and have some antennas there on the bottom that allow us to do that. And then we're really designed for no sun in the cup. So we try really hard to keep the sun and the Earth out of the cup of the thermal shield, and therefore also out of the telescope. And that really drives the way that we operate the observatory in the orbit. Of course, I want to talk a little bit about the payload here and that design, and I spoke to it a few minutes ago, that the central part of this design is that it has this cryogenic capability. But unlike a more expensive mission that has a cryocooler and fluid that slowly depletes over time, this does not have an active cooling system. So we actually leveraged a technology that was invented for the Planck mission many years ago, and it's hard to see in this graphic, but below the telescope there are 3 V-groove radiators, and this is what we got from Planck. These are geometrically designed plates that sit under the electronics that generate heat, and because of their arrangement, where from the center to the outside of the plate, they're always increasing in distance from each other, heat photons that are generated literally geometrically bounce out. And for SPHEREx, the innovation that we came up with was to actually extend those plates into these giant shrouds that both provide some light protection for our telescope, but also just extend that bounce out. And they're designed for 7 bounces of a photon from the bottom all the way to the top. And yes, we did measure that in INT to make sure that it had 7 bounces. And these were really the innovation that enabled SPHEREx to be so low cost, and I think actually are an enabling technology for future missions that want to do cryogenic exploration without a high cost of carrying a cryocooler. We really wanted to have a simple-to-build system as well, and so during development, we actually changed the design from our original proposal to have solid honeycomb shields that were easier to manufacture, and I think we really optimized this design for manufacturability, and that was a central part of delivering SPHEREx on time.
All right, so now changing our focus to the instrument itself. So at its core, SPHEREx is an enormously wide field of view telescope in the near infrared. It uses this 3-mirror anastigmat design. It's a very efficient way of pushing a lot of photons through your telescope with no obscured aperture. And we use a dichroic beam splitter to divert light to 2 simultaneous focal planes in the shortwave and the midwave infrared. It's an 11.3 by 3.5 degree field of view, which is an absolutely enormous footprint on the sky. At the footprint of the focal planes, we have on either side a 3x1 mosaic of Teledyne H2RG detectors. But the real power of SPHEREx lies in those filters. They're called linear variable filter spectroscopy that live on top of those detectors. Now you can think about a LVF, as we call them, as just a bandpass filter, except the wavelength that it transmits through the filter varies as a function of position on the sky. So if we think about how SPHEREx builds up a spectrum, we'll take our telescope, cut it in half, and think about the rays coming in from a source on the bore side. It comes to a focus at a point on your focal plane. That F3 light cone will transmit wherever it lands through that point on the filter. We know the wavelength of that filter, and so we'll get an image, we count up how many photons got liberated, and then there's your point on a spectrum. It's a single point. Of course, because we have a dichroic beam splitter, you're actually measuring that same source at 2 different wavelengths. Then the next step, you'll tip a little bit your telescope. That same source lands at a different position on the focal plane, goes through a different part of the LVF. You get a different image, add it up, and we have a different wavelength measured. If you repeat that 51 times, you generate the entire spectrum. So this is, if you thought about this just as I illustrate here for a single source, that's a really inefficient way to build up a spectrum, right? Because you have to do all of these pointings to build it up. But of course for SPHEREx, there is no off. We're making a spectrum towards every point on the sky. So you're multiplexing this by hundreds of thousands of times each pointing.
So this is a video of our orbit strategy, and I talked about how we don't want to have sun in the cup. We also don't want the Earth in the cup, and so you can see the structures there that represent our avoidance criteria. And this does make the pointing a little bit complicated. We have to have small slews to go from line to line in the linear variable filter, but also large slews when we get to a constraint, then we want to move away from that constraint so we have time to do little steps across it. And you can see a projection of our linear variable filter and those stripes on the sky and how we do the small slews and then slew to the edge of a constraint, more small slews until we get close to a constraint boundary, and then slew again to give us more space to do it. So it's not a push broom regular pattern like that, but it is an a priori design pattern. We know exactly what geometry we want on the sky, we know exactly what our avoidance constraints are, and so this was a really very simple, once we decide what we're doing and how to make that map on the sky, we just go up and turn the instrument on and tell the telescope to do it, and the pointings go. And so this is our orbit. Let me go to the next one here. And then speeding this up, obviously, we don't go this fast. We actually cover the entire celestial sphere because of our orbit and sun synchronous in about 6 months, and we do 4 complete maps in 2 years for our prime mission. And you can see, having sped up this video, how we cover the entire celestial sphere. It's not exactly clean at 6-month boundaries. Of course, the pattern is a little bit more complicated, but it's about 6 months for each one. And we actually offset the maps by half a spectral channel so that all of the interactions between the stripes don't cause janky things in our data. And so we get 2 complete maps offset by half a spectral channel, and that makes our giant map that we deliver for NASA. So I want to talk a little bit about the timeline. These competed missions, these small missions, have a really difficult path, and it takes a lot of perseverance. The first idea for SPHEREx started in 2012 with a science idea to do spectroscopy based on precursor missions that were looking at the cosmic microwave background from ground-based observatories, or ground-based instruments actually at Antarctica, and some sounding rocket projects that the cosmological lab at Caltech was working on. And so they came to JPL and said, hey, we want to actually make a space-based measurement of this, and so we got together and submitted a proposal to the Small Explorer program there for the first time. And we were lucky, we actually got selected. That evolution of that instrument design went through some tortured trade studies, and we finally arrived at a more simple version, which is very close to what we actually built for that one. And then we were selected for step 2, even the first time out of the box, and that was really exciting. We went into our step 2 for the Small Explorer program, and step 2 is hard. You have to really go to a greater level of design detail. It was our first time submitting, and so we had a lot of work to do to catch up to where we needed to be in maturity for that design. And right before we submitted this next step 2, the call for the MIDEX step 1 was due, the notice of intent. And so we had this dilemma. Do we just hope that we get selected out of step 2, or do we go ahead and hedge our bets and submit a notice of intent for MIDEX step 1? And so we hedged our bets, and in fact, we did not get selected from SMEX step 2, and went into step 1 for MIDEX and proposed another step 1. This is the Medium Explorer. And we did that for the 2016 call. And then we were fortunately selected for step 2 out of MIDEX, and we thought it was a slam dunk. Incredible science, almost fit in the SMEX bag, almost selected. And we had a little bit more money in the Medium Explorer call, and were able to really put that money toward risk reduction. So we did things like added more staffing to the data processing estimate, and we had a little bit more fidelity in the photon shields that design, and we did some more prototyping during phase A. And so this was really, I think, the best decision we ever made on SPHEREx, was to move it from SMEX to MIDEX. And it really made it so that this mission had a really low-risk implementation, and we were selected, fortunately, had a site visit. Here are all the versions of the proposal that we submitted. There's a lot of them, many, many pages behind this mission. And then this is an image at Caltech where we held our site visit, our formulation team there. I'm there in the middle. And it was a wonderful experience. One of the best things we did during that site visit, because it wasn't on base at JPL, is we held a party the day before the site visit and invited all of our families and all of our bosses, and everybody came out and looked at our stuff, and it just gave this jolt of inspiration to the team, and I think it really paid off at the site visit, because we had a really excellent site visit and felt leaving very confident. So of course, after you have the site visit, you wait for several months until NASA makes a final decision for selection, and we didn't hear anything until Thomas came out to JPL when we were saying goodbye to opportunity at the lab. So it was a big event at the laboratory, and he pulled the president of Caltech and our PI, Jamie Bach, into a conference room at the top floor of our administration building, and tweeted out that we got selected for implementation. So it was a pretty sad day for JPL that we were saying bye to opportunity, but also a very happy day because we were selected for implementation. So what happened in late 2019 when we started implementation is this thing called COVID got in the way of us getting ready for PDR. And at that time, in the preparation for PDR, we were doing a lot of instrument prototype development at Caltech in the lab. And of course, when we were in the lab and the lab was shutting down, we were freaking out because there was going to be an unknown number of months where we would have no access to our hardware in the laboratory. And so we actually had our team take a whole bunch of their hardware to their garages and their home offices, and we kept prototyping during that time, and did our preliminary design review in a fully remote fashion with everybody calling in from home, our review board calling in from home, and still trying to show that we were ready for confirmation with SPHEREx. And so this is the design that we had at PDR, and you can see we still have these segmented photon shields, so you know a trade is coming after PDR, pretty sporty.
All right, so then you know, with PDR in the rearview mirror, we moved on to the construction of the instrument through you know, a very staged approach. You know, starting at component level, getting those long lead items. There you can see a picture of me holding a flight linear variable filter, and I think that's a great example to show just the power of this design. That's the entire spectrometer, a few grams of sapphire held in your finger. There's no gratings or prisms or big dispersive elements. We went ahead with prototyping at the focal plane level and practiced kind of spectral calibration. Simultaneously working on the generation of the telescope. This was done with our industrial partners at Ball Aerospace, which is now BAES. You can see here in a photo of that telescope coming together and some of the optical testing we did at telescope level, just aligning the mirrors and understanding where the focus was with respect to the interfaces to where that focal plane housing mates to. So then you have the task of putting everything together and doing the final instrument calibration, which was really my bread and butter and kind of favorite time of the mission here. We had done a series of tests just at the focal plane level. You could see here an image of what that focal plane looks like with its back housing removed and all the thermal isolation stages. The detectors are pointing down in this picture. That was done at Caltech and JPL. As I just mentioned, the telescope went through its own suite of both room temperature and cold testing at Ball Aerospace, now BAE Systems. And that thermal system was coming together at JPL too. Here's a picture of the flight V groove. You can see 6 images of my face. And you know, that's the radiator. And when these things come together, we bolt it together into this configuration is what we consider the instrument. And it's a very powerful configuration for testing because it contains the entire signal chain from a photon coming in through the optics, detectors, filters, through the signal chain, the wire, the flight harnesses, and out through the interface to the spacecraft. So this was our instrument level configuration, and we needed to devise a way to do the accurate measurements that we needed to on the ground.
And I want to point out that when we got it into that configuration, that flight configuration of the instrument, we never broke configuration after that time. Absolutely. So it was a huge retirement of development risk to have it at that level of assembly and never change it from that point forward.
Right, so there were 2 big requirements of what we needed to test on the ground. First of all, you've got to make sure this thing is in focus. There's no active focus control on SPHEREx. It's got to be launched up there such that when it gets to its operating conditions, the focal plane is in the right position. And we need to calibrate the spectral response of the whole spectrometer. We need to know where each wavelength lands on each part of the focal plane. To do that, we devised this scheme in concert with our partners at the Korean Air and Space Institute. We did that, what we call it the Kazi chamber, and we concocted this scheme to do 2 configurations. In an optical mode where we could put the telescope operating at its flight temperatures, looking through a giant aperture to a collimator in the laboratory, as well as a dark mode with a big extension where we could couple in monochromatic signal to uniformly illuminate the field of view and reconstruct a spectrum. This was kicked off in December of 2019, just before our pandemic started. Here's our trip to Daejeon. You can see why the Korean Space Agency was such a good partner, because they had built previously a chamber for one of their near-infrared systems. It was less demanding, but they had the backing and made for great international partners with us. It was developed remotely across the Pacific as the pandemic came and kind of faded, and then by early 2022, maybe mid-2022, the chamber was shipped across the Pacific to my laboratory at Caltech. You can see it here on its delivery. Our lab does not have a basement level loading dock. What it does have is a removable section of driveway to get it down to its operation. You can see here we're lowering it down on the crane. And then we went through a commissioning phase. Here's our Korean team. Super happy because we got that chamber up and running in the lab at California.
And despite the fact that COVID started literally a few miles from their home institution, they delivered this chamber on time.
That's right.
I have no idea how that happened, but it was awesome.
That's right. So we also, not just the setup of the chamber, but we kind of built our whole facility for testing this around this concept. And what that was, is to have a clean facility, a class 10,000 clean room, directly across the hall with doors that are perfectly sized for the chamber and the instrument in it, to to the facility where we could actually do the optical testing. What that looks like is something like this, where you're working in a Class 10,000 environment. We can close up all the flight hardware, hermetically seal it, and then wheel it across the hallway where we could actually do the measurements without having to go through the clean room protocols. It was a much more efficient way than just having to live in a single room or do all of our measurements in a clean room, which is very onerous. A detail that I'd like to point out, I think a lot of this crowd here who work in the infrared are probably looking down, and they work at photocurrent levels that are, 10 to the 6 times brighter than what we're looking at when we're looking for signals from across the universe. So when we're coupling our telescope into the laboratory that's 300 Kelvin and just blasting us with infrared photons, we actually need to throw away 5 orders of magnitude of signal to control that laboratory and get our photocurrents to where we need them to be at a few to tens of electrons per second. So we developed this cold filter with sapphire with a tuned gold coating on it. And of course, this filter cannot introduce any wavefront error, or at least at a quantified level, so that you don't get the wrong focus. So this was implemented and worked really well. This is what it looked like in testing. We basically put a collimator and couple it through where you can move the pinhole at the focus of the collimator in and out of focus, moving a source from infinity and dithering it around. The data looks something like this, where we put a 5-point asterism. This is just a zoom into a tiny chunk of a field of view, and you can see that spot go from fat to skinny and back again. You get, if you're looking at your beam volume from the PSF as a function of focal position, if you've got your telescope and your focal plane in the right position, the smallest beam should happen when that goes down to 0, and you can see in this image we achieved that. This was done in a series of 3 cool downs. First, we go to our initial position, so you can see here for the short wave and the mid wave, initially what it looked like for the focal position with respect to 0, which is that gray plane where we're trying to get. We came pretty close, within 100 microns, just from dead reckoning. Metrology stack up, including corrections for cool down and refractive index changes as a function of temperature. Open it up, realign the focal plane to where we measured it should move, cool it back down again, verify that it's where we want it to be, and then we shake it. We shake it with launch load vibrations and make sure, after we cool back again, after vibration, that it has not shifted. We then move on to our spectral calibration testing. And I do love these pictures because I think this configuration is our most Bond villain looking like device that we concocted. And of course, the job of the Winston cone and integrating sphere is to accept a monochromatic beam of light and project it uniformly across the field of view of our telescope. This is what that measurement scheme looked like, piping in our single wavelength light. And this is what our data looks like in this movie. You can see that stripe moving across. Now, even though the entire focal plane is being uniform illuminated, you only see a stripe going across because the filter is doing its job, and it's only letting the wavelength of the light through at the position we want it to be. So as we move to longer wavelength, you see that stripe moving along. We do this across the entire wavelength band, tediously, generating a spectral response function for each of our 2040 by 2040 by 6 pixels. It's 24 million pixels. Each one has a curve that spans 5 orders of magnitude in dynamic range. And then from the central wavelength, you fit to those response functions, and you have a calibration map that looks like this. This is the map that tells you when I'm measuring a source on the sky and it lands on a given position, what wavelength is it at.
So in the meantime, we were at JPL building up the thermal system, and so this is the fully assembled photon shield at the end. It's silver on the inside because we want the shininess and optical surface there, but on the outside we want it to be white so it has great thermal properties and doesn't change its shape while we're in space. And here's a picture of my 5-foot-tall instrument engineer standing next to the photon shield. So it is tiny, but she's even tinier. And then I think one of the scariest days on SPHEREx is when we did the vibration test of the photon shields, and yeah, it was pretty scary. You can see that each of the shields hits its resonant frequency, which is different from the other ones, and so they don't move together, they move against each other. Obviously none of them touched, and we passed with flying colors. But it was a pretty terrifying day, and we have, I think, about 85 videos and fingernail scars in our palms from watching that happen. And then at that time, we were ready to ship the photon shield and its container and the integrated payload after its series of thermal vacuum tests to BAE for observatory integration. So we put them in the back of a truck and drove them to BAE in Boulder for the start of observatory INT. And then I'm just showing a couple of advances of the design as it matured over the life cycle, getting ready for observatory INT, and then in its final configuration that we assembled at BAE. And I will say that our BAE systems partner is outstanding at INT. It went extremely smoothly. We, after having the payload in its final performance checked configuration, we were able to integrate it just as we planned, put on the photon shields, and then get this beautiful integrated observatory photo on our turnover fixture. And you can see the telescope there buried inside the photon shield, and one of our BAE technicians standing there. BAE takes the best pictures in the business, seriously. They always have these blue and red lights, so pretty. But it was a really great time. And then once we were assembled, we went through our standard environmental test suite, including vibe and acoustics, with Maryland Sound coming in with the speakers to give us that launch acoustic environment. And everything went pretty well during that testing. And one of the key things that made this go so smoothly is we had that COSI chamber back at Caltech, where we had done all of the hard cryogenic thermal testing already on the system. And we qualified the photon shield for its operational temperatures, put the instrument through all of its paces, and did not change its configuration. So then at the observatory level, we could do a pretty classical, only down to 100 Kelvin kind of test, not having to do expensive GSE, not having to do a whole bunch of time to get down to that temperature. And so we really took advantage of the facilities at BAE to do a smooth observatory campaign. And in the end, we're ready to ship to the launch site. And SPHEREx, fortunately, got to launch out of California at Vandenberg Space Force Base, just a few hours from JPL. This made it really nice for us to be able to drive back and forth if we needed to. And of course, SpaceX, also close to their home office down in Hawthorne. So we had a great time there on the coast, and we're slated to launch out of Slick 4. And you can see where the prime real estate that Vandenberg occupies on the California coast. And then Slick 4, where we were slated to launch from. We processed at the Astrotech processing facility on Vandenberg and drove there from BAE, taking a kind of southerly route so that our tall enclosure didn't have to go under low overpasses. And we got there smoothly, and this is the day of arrival. Sadly, at the same time, fires were raging across Altadena, right close to JPL, and we actually had some team members who lost their homes, some team members on the convoy that lost their homes while they were driving to Vandenberg. So it was extremely challenging. In addition, because of the fires, the path that the observatory had to take from BAE to California had to go all the way down to Texas because there were fires raging across the Southwest, and the air quality wasn't sufficient for our environmental control system to actually survive and keep it clean. So this was a huge impact to us, not only just because there were team members directly affected, but it actually changed our operation to some extent and extended our path to get there. This is a real picture from our Flight Project Center where our project offices are at JPL, with a fire in Altadena right behind it. So it was very close. At Vandenberg, we processed with our rideshare payload, and this was another science mission. I think this was the first time that 2 science missions were launching on the same rocket, and we had the opportunity to process actually in the same clean room at Astrotech with Punch and heliophysics mission. And you can see the 4 Punch spacecraft mounted on the interface ring at the bottom, and then our spacecraft sat on top, and then all of us on the launch vehicle adapter that goes on the top of the Falcon 9. We actually had quite the experience with Tetris in that clean room, getting GSE around and coordinating that, but it was wonderful. We actually really got to know each other really well. We gave a lot of joint science presentations in the local community. We advocated for each other if one had an interface issue or we needed support, and it was really a wonderful experience. And I know this was a huge cost-saving measure for NASA, and so two science missions for the price of 1 launch vehicle, and I'm all for it. It was a wonderful experience, and I think we were great rideshare partners. We were very complementary in terms of accommodation requirements inside. We wanted the same kind of environment, the same cleanliness environment, and so we were actually really complementary, and that's why we rode together. Then, right before launch, we had to encapsulate. We actually had to do it twice because the fairing had a leak after the first one, so I say encapsulation is really great the second time. And this is kind of the last picture of the integrated stack before we got on the launch pad. Then we worked really hard to get this opportunity to take some pictures with the rocket vertical on the launch pad. This is not something that happens very often. As most of you know, the Falcon 9 schedule is really fast getting to launch. And so we took, unfortunately, a break and got to have most of the team there to take some pictures. You can see our PI and Phil there in the bottom left, and then my awesome girl crew here on the right side that spent most of the time at the launch vehicle processing for the entire campaign. And then this is a picture of our entire integrated team that was able to be at the launch site. A really precious picture, and I think it will be one of those we put in our reels for a long time. And then our launch. I think you can't hear the sound, but it was a picture-perfect launch from Slick 4. Oh, here you go.
SPHEREx and Punch on their way to map out our universe like never before and revolutionize space weather forecasting.
Stage separation confirmed.
And back ignition.
Stage 1 boost back startup. Coming up next, we will see fairing deploy, and that's when the two fairing halves will separate and expose SPHEREx and Punch to the atmosphere of space.
Fairing separation confirmed.
In about 30 seconds, we will have payload deploy of SPHEREx.
SPHEREx separation confirmed.
SPHEREx is drifting away from Falcon 9's second stage, confirming deployment. The mission isn't over yet. Falcon 9's second stage is still carrying NASA's Punch mission.
Separation confirmed.
Wow, look at that. To actually see them, that's great.
So we actually had successful initial acquisition, both us and Punch, on the same day of launch. That was wonderful. The video actually was never a requirement in our launch vehicle interface agreement because they weren't sure we would have enough bandwidth to get it. So we're really happy to get video, and it was pretty awesome.
Yeah. And you know, one amazing thing about launching in Southern California is you could just see this from LA. These are some friends of mine in their front yard in Burbank, just watching SPHEREx go.
It is
go
like
off.
taking a video, guys. Say hi to Phil.
Yeah, to Phil. It's really crazy. You can see these things from home. You know, just this event that we've been thinking about for decades, and it's just from LA, from the front door. You could see that.
And then, of course, how often do you get a picture of your spacecraft drifting away from the launch vehicle? But this is how great our injection was from Falcon 9, that the upper stage stayed so stable behind us that we could get this beautiful still out of the video, and just beautiful to see it there, the limb of the Earth glowing. Of course, every thermal person like, don't turn that way, don't turn that way. Anyway, it's a great picture and was a wonderful sort of warm fuzzy that we had when we were getting ready to do initial acquisition and start the in-orbit checkout.
Right, so we then transitioned with SPHEREx happily up in orbit to our checkout phase that spanned from March and April. Here's where we ran everything from in what we call the EOMOC, the Earth Orbiting Missions Operations Center. It's at JPL, and we proceeded with the cool down. Now, I hope you'll bear with me. It's a little bit down in the weeds to show a housekeeping plot in a plenary lecture, but I could give a whole lecture on this plot, how amazingly well our passive cooling system worked. You know, there's using only the coldness of deep space. We're cooling down. Each variation in this has to do with an attitude change, with letting more or less Earth into the cup. We went through decontamination and cooling down. You can see those dashed lines indicate our pre-flight desired temperatures, which we hit spot on. If I change the x-axis of this plot and just look through, goes up to like a few weeks ago, how rock solid that is. And if you want to quantify and just really zoom in on those two temperatures for our shortwave and midwave, look at the y-axes on these plots. It is stable to an RMS of 10 microkelvin across months. And I can't wait to make this plot where that x-axis goes
Passive cooling.
2 years. This is actively controlled, but it's passive to get us down there, yeah.
I mean, for us, the passive cooling was so important, and the reason we liked it so much and we're so careful with it during IOC is because going in the right order to make sure we didn't get water on the optics was really important. And it's, you know, it wants to be cold, and it wants to be cold right away. And so we had to do that very carefully, and I'm so proud that it was just a really great collaboration between science and engineering to make that successful.
Absolutely. So then we got to the fun stuff of actually, after commissioning everything, we get to power this thing on and see what does it see. Okay, so I'll walk you through what you're looking at here. Remember, SPHEREx is an enormously large field of view. So that's an 11.3 by 3.5 degree, 3-band image. And of course, we have a dichroic beam splitter, so you're looking at the same chunk of sky across the beam splitter in 2 different wavelength ranges. So in this image, a few things pop out immediately. First of all, you see that stripe that goes across the short wavelengths there. That looks a lot like the spectral calibration images I just showed, and that's because that's helium air glow in the upper atmosphere. So our first exposure that we took with you've already got new science. It's not astrophysics that we were going for, but we're learning stuff about the upper atmosphere of the Earth. The color here denotes wavelength, so you're looking across spectral images, so we can see. These are spectral images. Each pixel has a different wavelength. And if we start zooming all the way in, you see there's a nearby galaxy. And if you zoom in on the zoom in, you can see those little faint dots back there. Each of those dots is a distant galaxy. And this is a single exposure. We take 600 of these a day, and we do that every day for 2 years in the baseline mission. As we went on, this is just from commissioning the early first light images. It was very clear just initially that the thing is working exactly as designed. It's absolutely in focus, and the sensitivity is right in line, if not better than what we had predicted on the ground. Some of these are spectral images, and you can start to see just how different the sky looks at different wavelengths. There's so much information in here, we're just scratching the surface. We began scanning with SPHEREx, and if we look at a diffuse cloud like this one on the outer coastline of the Large Magellanic Cloud, and we look at it as SPHEREx sees it natively, and we now turned it into a movie where we're taking little steps. So the same part of sky, now we're fixed in celestial coordinates, and you see the movie changing shape as we go in, and that's because different wavelengths are landing at different positions on the array. So what you're seeing now, what looks like waves going across the sky, of course these are fixed, it's just measuring different molecular emission lines. You're seeing ionized sulfur as well as PAH, or polycyclic aromatic hydrocarbon. You can think about that like stinky diesel exhaust fumes. But just this is 8% of a data cube towards only this one pointing. As SPHEREx gets better and better, moving along, we're starting to build up our deep fields at the ecliptic pole. So here's a co-added down image, but of course what makes SPHEREx amazing is not individual images. If we look at one spot on this where that X happens to be, we zoom in on a planetary nebula. Now in our movies, you can see by the title, each frame of the movie is a different monochromatic image of that one object. And as we scan through, you can see the geometry totally changing. And that's because we're seeing the different emission lines light up, the different hydrogen series that tell you about the ionization fraction as a function of radius, the temperature, the Pfund series, bracket alpha. There's all sorts of stuff that's just in this data set. And I'm just not talking about the science of the planetary nebula. I'm just using this as an example of how much you learn through the power of spectroscopy. And if we take a different look at this, and really start to think of it as a data cube. We look at that just a few degrees across, and now we're spinning around, going from 0.75 microns out to 5 microns, and every pixel, you're seeing the spectrum of whatever's in there, just projected along. It's like pages in a book, and we're flipping around to the long wavelength side. This is just a few degrees aside. We're gonna do this for every pixel on the entire celestial sphere. And this is how we're doing so far. Just since we've started in May of this year, we've now built up spectra. Every pixel in this is the entire sky projected out. Think about like when you look at a map of the Earth. And you can see here just we're marching along and making spectra of the entire sky. So this data is now starting to go out to the public. It's served at NASA's Ursa. It's really amazing. We've had over 1 million files downloaded in just a few weeks since this started going out, so it's really exciting. I can't wait to see what the community comes up with in this data set. Our baseline is for 2 years of observation, but of course that could be extended. And then we've got another year to get to the exciting extraction of the cosmology goals, the extragalactic background goals. And just to vaguely give a teaser, I'll just say that we're already writing initial science paper, because there are when you have a new capability like this, there were so many things we just see with our eyeballs in this data coming out, and you're like, nobody's ever seen that before. There's some amazing low-hanging fruit that we're writing papers kind of immediately. So with that, we're gonna thank everyone for listening. It's been a real pleasure to be here at Ascend, and we'll welcome Charles Norton back up to the stage.
Oh, thank you so much. That was just a really wonderful overview, Jennifer and Phil. There are QR codes on the screen and on your table, so if you have any questions for Jennifer and Phil, please submit them. Should we stand over here? Why don't we stand over here for photography time? We can take a seat as well. Oh, thank you so much. I just really love hearing about the mission. So we do have a couple of questions which have come in. Two technical, one more scientific. So regarding the photon shields and their sizing, were they sized primarily by the mission thermal requirements, or were the launch vehicle fairing constraints a factor as well?
So the predominant goal is about keeping our telescope in the shade at the right geometric angles. If you actually see that picture of the encapsulation, we're tiny.
Plenty of space.
in a Falcon 9 fairing. And this actually goes back to our heritage when we were originally designed as a SPHEREx. Our first design had deployable photon shields because we were going to fit in a Pegasus launch vehicle. So we scaled up some things, but we had plenty of room, and that turned out to be a fantastic thing for NASA because they got to use some of that extra fairing space to launch punch along with us and get two launches.
The primary driver for the size of the photon shield was a combination of thermal. We wanted, as I said, 7 bounces with the geometry of the infrared photons going out, and also we wanted a certain amount of space above the top of the telescope so that incident light could not get in, and so that really sized it. It had really nothing to do with the launch vehicle. You could fit 3 SPHERExes inside of a Falcon 9.
Wonderful. Yeah, actually, I learned in your talk, I didn't realize you didn't have any cryogens either, so that's
no cryo.
It's really quite impressive. There's another question here. It says, after a lot of JWST errors, how accurate is performance wavefront aberration error analysis with coronagraph beam splitter? Reading exactly as typed, but if I were to try to paraphrase, I think there's probably just a question about, how accurate and how well you're meeting your performance requirements, which from what you just stated,
yeah, it's
to be overperforming.
It is performing excellently well. It's a different beast than James Webb, right? We're a huge survey telescope as opposed to a very fine, detailed zoom in. And our wavefront error requirements are very different than what James Webb did. James Webb had a very complicated in-orbit focusing mechanism, including aligning their segmented mirrors, right? We're single monolithic mirrors, all made out of aluminum. And the beam splitter alignment maintained beautifully. We are well within our tolerance, which was something like plus or minus 20 microns. So think about it, positioning by dead bolting after cooling down to a tenth of a human hair width, and it held beautifully on launch.
Excellent. I have one more question here. Are there other astrophysics missions that will be enhanced scientifically by SPHEREx data?
Absolutely. So I think, maintaining with the James Webb analogy, right, we are industrial scale spectroscopic mapping. So for instance, for finding our water ice absorption targets, James Webb has fantastically powerful spectrometer on it in a similar wavelength range, but of course, the slit size is absolutely tiny on James Webb, right? So you just couldn't go searching for things. With SPHEREx, you can go search for things, say, that's an extremely interesting target, let's go follow it up with James Webb. So there's this kind of dynamic range interplay there. You know, there's other missions which are, you know, have scientific overlap, which all kind of contribute something different to the table. You know, like for instance, Euclid, or the upcoming, of course, extremely powerful Roman. These will go much deeper than SPHEREx, targeting a different redshift range of large-scale structure. But of course, they don't have, Roman doesn't have spectroscopy. It's an imager. So, you know, they have better light collecting capability and can see deeper, smaller pixels, but we have the spectroscopy. So there's a lot of synergy that will happen between SPHEREx and other scientific missions.
And Charles, I think one of the things that our science team has always said from the beginning is that the most exciting result or scientific discovery from SPHEREx is likely something that someone on our science team has never even thought of. That's the power of this kind of data set for the whole community, is that it has such depth and such breadth that, you know, one scientist is never going to take advantage of everything that's in that data set. It's probably going to fuel discoveries in astronomy and astrophysics for a decade or more, similar to other all-sky surveys. And in this case, because of that spectroscopic record that advances from the handful of channels that previous missions have had to 102, you know, full spectra of SPHEREx, it really is a great data set for all of astronomy.
Oh, wonderful. We may have time for one more question, although a lot of questions just came in. What would you consider to be the most difficult or stressful moment during the mission development for SPHEREx?
Wow. Well, that's a great question. I mean, the obvious answer is when COVID hit and we all had to leave the laboratory. But I'll give a more, you know, we had to be very dynamic in our iterations between testing and what our goals want to be. You know, we really care about things like control of stray light. And, you know, we had, I would say, one very stressful time, we were doing these simulations of the way stray light will go through, and found kind of a glint that was a little bit of a head scratcher. We said, where does that come from? And we found there's details in the shapes of the frame, you know, the baffle edges. And what you really want to build is, you know, something that's infinitely sharp and infinitely black, which is just not easy to do. So we underwent a full, you know, we iterated around, you know, painting a knife edge black is not an easy thing, and cooked up a recipe to make that happen, and we reduced that effect by several orders of magnitude. So from a technical standpoint, that was my favorite kind of victory. You know, we got some wild cards and reacted in real time, and the performance on orbit is excellent.
Yeah, and I think COVID is really the predominant thing. We delayed our launch by about 9 months because of impacts from COVID. We had a lot of trouble with supply chain. Our primary structure was really delayed because we couldn't get access to aluminum. Our photon shields are huge, and they were being processed at a plant in Northern California whose, you know, primary job is to build the tops of warheads, and that's obviously a higher priority than this little science mission. And so that was prioritized over ours. And so we really had to work a lot on the INT schedule to get those photon shields delivered and into observatory AINT. So, and all of that was kind of, you know, fruit of that COVID tree, and it was really difficult. I mean, it hit us right at the time of getting the design from, you know, its preliminary state to final design, and then starting to manufacture. And that's when you're placing all of your orders, you're trying to engage all of your, you know, your subcontractors, and it was challenging, not just for us, but for our partners as well.
Oh, well, thank you both so much. It was just a wonderful experience to hear these details about the mission. It's a tremendous team accomplishment, and we're just so excited about the results and what we'll learn and what is coming in the future. So on behalf of AIAA, I'm actually pleased to present 2 certificates to each of you, just, you know, celebrating both the lecture and the contributions you've both made. So thank you very much. It's a pleasure to see you both, Jennifer.
Thank you so much.
Thank you so much.
Thank you.